This is part two of a video, and this time we're going to try and apply it to light. The Doppler effect with sound, the example we used was 343 meters per second, which is the speed of sound in air. Air is the sound can't travel unless you have air, so you have to have air if we're going to talk about sound. It can also travel through solids and things like that, but you have to have what's called a medium for those waves to travel. In that example, I tried to choose a speed of the source towards the observer that was enough that it made some fairly big difference in the tone. For instance, we had a 1000 hertz tone, and from the observer's point, it was 1068 hertz. (1069 hertz). So, wouldn't that same thing work with light? Light is a wave, and if you have something coming towards you that was sending out a particular source of light, then wouldn't you be able to detect the fact that it's coming at you? Wouldn't the frequency change? How would you sense that the frequency of light changes? Well, that's your eyes. Your eyes do that. So, would the color of the light change if it's coming towards you? Okay, what's the speed of light? 3 times 10 to the 8 meters per second. That's 300 million meters per second. 300 million meters per second. So if we're going to see a change in the color of light, we better get fairly close to 300 million meters per second. So just to come up with an example that matched the sound experiment, that would mean I would have to have the source of the light coming towards me at something like 20 million meters per second. So I can compare 300 million meters per second to 200 meters per second. So what's the frequency of light? Well, frequencies of light are like 10 to the 14 hertz for your eyes to see it. And I'm going to use one of the lower frequencies so that the light frequency can increase. I'm going to choose a red laser with a defined wavelength. We can talk about the frequency too. And I'm also going to talk about the speed that is coming towards us. Now, if it's coming towards us at 20 million meters per second, we're not going to be able to see this on Earth. This is going to have to come from way out there in space, because 20 million meters per second, if it's anywhere near on Earth, it's just going to go by us real fast. We can't see anything. So let me talk about a possible scenario where this would happen. So you might say, oh, okay, that's where this blue shift and red shift comes from that astronomers talk about. The Doppler effect is one idea. There are 4 or 5 main ideas of theories that's causing that, other than the Doppler effect, and many, many more. And the controversy still continues. One of the differences is light doesn't need a medium to transfer. You can see light through the vacuum of space, so it doesn't need a medium. And the speed of light is very consistent. Now, you can slow down light when it goes through glass, because that's how lenses work. But the light between the molecules inside the glass is still moving and being retransmitted. So that's how the idea that light can actually be slowed down. It's only our reference to what kind of material that light happened to be going through. And of course, light can be stopped. You have an opaque object that there is the light, it's already stopped. Here's the scenario. Here's the observer. Here's this yellow ball, which we'll call an asteroid. In other words, it doesn't emit light on its own, but it has a laser mounted to this asteroid. This asteroid happens to be moving at 2 times 10 to the 7th meters per second. So that would be 20 million meters per second. And this is the speed of light, 300 million meters per second. So let's figure out, as if the Doppler effect was the change in color that this observer Here's some calculations I did. The frequency of a laser that's 650 nanometers, that's usually the way lasers or light is usually listed in wavelengths, but what I'm going to do is put it in frequency. This C represents the speed of light. C is the constant used for speed of light. Here's the wavelength, the 650 nanometers, which is the same as 6.5 times 10 to the minus 7. And here's the speed of light, 3 times 10 to the 8th meters per second. That gives us 4.6 times 10 to the 14 hertz. So that, think about that. That is a really high frequency. Whoa, there's a bunch more calculations. Okay, frequency or period, in other words, the time it takes for one cycle can be figured out by 1 over the frequency. And this period is 2.17 times 10 to the minus 15 seconds. Very short time, very short time. So if we take that period, in other words, this is how long it takes for the one 650 nanometer cycle to occur, because that's the wavelength, we already have that. If we take the speed of the asteroid, which is this 2 times 10 to the 7 meters per second, and multiply that times this period, we get 4.34 times 10 to the minus 8 meters. Now, that 4.34 times 10 to the minus 8 meters is less than the, let's see, where is it? Is less than the 6.15 times 10 to the minus 7. So if we take those two values and find the difference between them, we'll see how long the new wavelength is. And the new wavelength is shorter by 6.07 times 10 to the minus 7. That gives the frequency by the observer of 607 nanometers. Now I've done this in green because the frequency should be something closer to a green value. And actually what we've done is shift towards the blue. So let me look that up and give you one more view of this before we close out on this topic. Okay, I guess I was a little bit wrong there. We didn't quite get to green. Here's where we started, was about 650 nanometers, a nice bright red. And as the wavelengths get smaller, then we get closer. This is about where we were, so it'd be kind of an orange. If we chop it down more, then we get to the green over in here. And finally, when you get to this end, you're at blue. So that's what happened. We went from this color to this color. So it looks a little more orangey here. Now imagine just those little shifts. That's not a very dramatic shift in color, and yet we're going 20 million miles, 20 million meters per second. So we're getting kind of close to the speed of light. So unless you get kind of close to that, you're not going to see a big shift in color. But this is just one of the effects that is suggested for why we have different color shifts. Rather than get up there and wave my arms and so on like I normally do, I'm just going to show you some pictures here that'll help us understand that Doppler redshift is not the only idea that explains or measures how fast the universe is expanding or other astronomical things like that. So here's the known redshift mechanisms. Doppler redshift, we just went over that. Now, gravitational redshift. Gravitational redshift is, according to general relativity, that when things get near a massive object, that the space is bent like that. And the other one beyond that that is recognized today is cosmological shift, where the idea is that the space between the objects is actually expanding, and not the objects themselves moving, causing the redshift, but an actual the space and time expands. Pretty weird, huh? But Doppler shift is not the expected idea when we're talking about cosmological things. Okay, here's cosmological redshift. Expansion of the universe is one of the known redshift mechanisms, and this is the big idea for the Big Bang idea. Okay, what are alternatives to that? Alternatives? Well, isn't that it? Either cosmological, gravitational, or Doppler. Why wouldn't that be all of them that we're talking about? Oh my gosh, let's look at some of these other ideas that are not Doppler redshift or gravitational redshift or cosmological. Here's back in 1909. They had a effect, and it had to do with sunspots that they were studying with astronomy. So that was that's slightly after general relativity came back. Compton scattering. This guy won a Nobel Prize winning theory that shows which causes spectral shifts. Critics say, oh, but that's not really it. It's blurring, which is not seen in the redshifts of distant objects. Now, here's a really good one, and these are fairly accepted ideas. Tired light. What in the heck is tired light? Photons move through space, they lose energy. So they actually lose energy and their wavelengths increase. Critics say there's several problems with this in explaining the Hubble law. It is not accepted by mainstream cosmologists. Okay, there's another one. Now we're getting more current. 1955, photon radiation density and path length. Another idea. Here's 1972, effect of mass on frequency. So this is kind of the intrinsic idea, is that the mass actually affects the frequency. So what we're looking at is differences in mass. Then here's another one in 72. Then here's another one in 72. Now here's another one in 72. Now here's another one in 72. So people are really fighting with this. Now remember, this actually helps people understand the expansion of the universe, and it depends on which theory you have as to how big the universe is. So you can see that science doesn't really know what they're doing all the time. They have all these different ideas. Okay, it keeps going on, keeps going on, keeps going on, all the way down to 2004, Here's Charles Gallow's neutrino redshifts, a proposal to look for redshifts in neutrinos, the little subatomic particles. And finally, the last idea here is a kinematic origin of cosmological redshift. Let me just try to summarize this really fast. Is that he's saying that these are actually Doppler shifts, but when we're talking about light, they're infinitesimal Doppler shifts. The stretching of space interpretation obscures a central idea of relativity, namely, is always valid. When was this done? What was the time period for this? 2009. That's only less than 10 years ago. So there's a lot of controversy about all these different things with redshift. Okay, so with electromagnetic waves, Doppler effect, we forget about it. Wrong. How about police radar? Police radar, which the FCC, Federal Communications Corporation, says that they allow police radar to operate in the 33 to 36 gigahertz range. So what I've done here is come up with a target like a car that we can reflect the radar waves off. Here's the 22 meters per second, which is about 80 miles per hour. Oh, I thought that was 80 kilometers. No, it is 49 miles per hour and about 80 kilometers per hour, which is what we had with the sound thing. So it isn't practical for to use sound when we're trying to figure out speed of a car. Somebody's trying to go faster than they should. But you can kind of see here's the frequency going this way, and the frequency coming back is going to be a shorter wavelength. Or a higher frequency, just like with sound. Look at the little bitty difference that radar detector has to come up with. 35 gigahertz, 35 billion cycles per second. That's a lot different than 10 to 14 that we did with the light. So here's the difference frequency and what they call the beat frequency, or that you can see that's just a subtractive difference between these two. So there we have with police radar. Are we done with things? No. How about weather radar? Here's weather radar, and it reflects off things. Is the weather radar looking at cars? No. They're not looking at cars. They're looking at things like raindrops. So here's an idea where the raindrops are moving away. So we had a red shift. So the storm clouds are moving away. We can track how fast things are going, or we can look at the raindrops of the coming storm as going closer, and you can see the wavelength of the green is less than that. So when it comes to low radio frequencies, the Doppler thing is pretty much accepted. It gives us good results, so let's go ahead and go with the Doppler. When you get to the things that are trying to measure things close to the speed of light and redshifts out in the cosmos, well, maybe that doesn't work so well. I hope this gives you a pretty good idea of electromagnetic wave with Doppler shift. And I was actually trying to go into the special relativity range, but that'll be for another video.